Hi everybody, today we're going to talk about analyzing and sketching a more accurate graph of a polynomial function. We are going to specifically be working with a calculator to be able to do this today. You guys have had exposure to finding different features of parabolas, so we're going to add the knowledge of finding those features of parabolas and pair them with finding features in polynomial functions. So in the previous lessons, we've talked about limit notation and roots and how to graph a rough sketch. But now we're going to be able to graph a more accurate sketch. So we're going to take what we already know with the end behavior, the roots, the y-intercept, and we're going to find more detailed information utilizing our calculator so that we might be able to figure out domain, range. Turning points have to deal with a lot of different things, including the intervals of where the graph is increasing, where they're decreasing, and finding the relative and absolute extrema. So to talk a little bit about definitions of some of these things before we get into doing some examples, a polynomial is increasing if it has a positive slope. So if we look at a piece of the graph and it looks like it has a positive slope, we would call that increasing. On the other side of that, if we look at a piece of a polynomial and it looks like it has a negative slope, we call that decreasing. So when you go from increasing to decreasing or decreasing to increasing, that is known as a turning point. So turning points can then be classified as extrema. There's two types of extrema. There's maximums and minimums. Now we talked about maximums in the context of a parabola when the parabola opens down, and we talked about minimums when a parabola opens up. So these polynomials will just have moments of upwards facing and downward facing parabolas. So hopefully, knowing what you know from parabolas, you'll be able to identify the minimums and maximums for any type of polynomial. So we have two different types of extrema. We have absolute or global extrema, which means this is the highest or lowest value that the polynomial can possibly have on the entire domain. And one of the things that I need to note is that we don't state infinity as an absolute extrema. Absolute extrema only occur on even exponent polynomials. So your x squareds, x to the fourth, x to the sixth, etc., etc. When they have an odd exponent, their domain is always negative infinity to infinity, which means that there is never an absolute low or an absolute high for that kind of polynomial. The other type of extrema are called relative or local extrema. That's any highs and lows throughout the entire graph. So you can have more than one relative max, you can have more than one relative min, but you're only going to ever have one absolute max or absolute min. So some key buttons on your calculator that we discussed back when we were talking about finding these features on your parabola. First, you need to make sure you type your equation into the y equals button. Typically, we type that into the y1. Press window to adjust your dimensions so that you are able to see the entire graph. Your second calc menu is very important. When you press second calc value, that's to find any y value. We use this specifically for y-intercepts. Second calc 0 helps you find the roots if your polynomial is not factorable or not already factored. Maximum finds your relative or absolute maximums. Minimum is to find the relative or absolute minimums. Both of these are considered turning points. So this has been mentioned before. You probably have encountered this while utilizing your calculator for this type of stuff. Your calculator uses scientific notation. Sometimes your calculator overcalculates and is a little bit too specific, meaning you get some answers that are -2 times e to the -10, which is just scientific notation for a really small number, which just means it's 0. So don't confuse yourself. If it's -2 e to the -10, it is not a value of -2. It's actually a value of 0. Jumping into a couple of examples, I'm going to move over to my calculator for a second so that we can take a look at this from a calculator's perspective. So right now I have both of my examples in here. So if you don't want to have more than one in here, that's okay. But just for time purposes, I put both in here. I only want to look at the top one, the Y1. I only want the blue graph to show up. So what I'm going to do is I'm going to highlight the equal sign, press enter, and that's going to turn that graph off for now so that I only see the blue graph. So going into my window, this is set differently from before. So one of the shortcuts that I use is zoom and then standard, which is 6. So this brings it back to a 10 by 10, 10 to the left, 10 to the right, 10 up, 10 down. We can obviously see that this is not low enough for us to see the whole graph, which means that I'm going to have to change my Y min. So go back to my window, go down to my Y min, change this to, let's say, -30, and let's graph that one more time. Still not enough. And -60 seems to have done the trick. So now we can see this whole graph. It is a cubic function. So this does have the shape of a cubic function where I'm not expecting to see any more curves in here. To think about it, if you have a cubic function, your number of turning points is typically 1 less than the exponent. So if we have an x cubed function, we're going to see this guy change directions twice, meaning 2 bumps. So this is an odd function, meaning an odd exponent. So we do have our end behavior go from down to up, from -infinity to the left and +infinity to the right, which means we don't have any absolute extrema here. So the extrema that we're going to find are both relative. So let's first find our y-intercept. Second, calc, value. What's the value of a y-intercept when x is 0? So our x-intercept is -2. Some of these things you are not going to need or feel like you need the calculator for, because as you can see up here, the function is in standard form, so we know that the y-intercept should be -2. But if we give you the factored form like we are in the second equation, it's a little bit easier to have your calculator find that value for you. So the y-intercept is not the maximum moment here, so we have to go back into second, calc. Let's find our maximum. So then let's find our minimum. Second, calc, go to minimum, and there is our minimum. The last thing that we need to find, or one of the last things we need to find, is a 0. It doesn't matter when you find these things. I'm just showing you the keystrokes to be able to refresh your memory on how to find these things. So the last thing that we need to find is the x-intercepts, or the roots, or the zeros. For this one, there's only one moment where this crosses the x-axis, so we only have to do this once. If your polynomial is not factorable, you'll have to find all of your x-intercepts by this method. So you may have to do this more than once. This one we only have to do once because it only crosses the x-axis once. So an x-intercept, also known as a zero, so we're going to hit 2, and then there is my 0. Now notice this is not a perfect 0, so that means that we probably weren't able to even use rational root theorem to be able to find this. So we have this 0. You see how we have 1e to the negative 12? That just means my calculator is overcalculating, and that value is 0, which makes sense because we tried to find a x-intercept. We know an x-intercept's y value is 0. So now I'm going to take a second, copy all this information down on the page that we just left from the Smart Notebook. So as of right now, for this polynomial, I have the y-intercept that we found, the x-intercept we found, and the 2 turning points. We've already determined what the turning points were based off of the calculator selections that we made. The max value is negative 1.483, and the min value is negative 57.035. Again, these are relative, not absolute. There are no absolutes because of the end behavior for this, which brings me back up to here. It is an odd degree with a positive leading coefficient, so our end behavior is, as x goes to the left, our graph goes down, and as x goes to the right, our graph goes up. So this is our end behavior. So after knowing end behavior, I'm going to do a real quick sketch so then we can talk about increasing and decreasing. So plot your y-intercepts, your x-intercepts, and your turning points. Utilize your end behavior. You already know what it should look like from your calculator. So take a second and sketch this. Alright, there's a general sketch. Looks kind of like what I saw on my calculator. So if we take a look at this, we are increasing from all the way down here up till my maximum, and then we start to increase again after the minimum all the way to positive infinity again. And then the decreasing happens in between my max and my min. We're decreasing from this max value to this minimum value. So when we report our increasing and decreasing, we really have to make sure we're utilizing our x values. We use our y values when we are reporting extrema. So we are increasing from negative infinity until that maximum moment. X value of our max was 0.263. And then we started going down till we hit our min. So we start increasing after our min, which was at 5.070, all the way to infinity again. And so we recognize that we're decreasing in between here, in between these two values. All right, since this is an odd function, meaning an odd degree, our domain and range are actually both negative infinity to positive infinity. So the main things to find are the mins and maxes. You can determine whether they're relative or absolute. After you find those in your calculator, you can use your calculator to help you find your y-intercepts and your x-intercepts as well. From there, your turning points can tell you extremas, increasing and decreasing. They also can help you with your range. Your domain for all of these will be negative infinity to infinity. Your range will differ depending upon if it's an odd degree or an even degree. So let's do one more example.